Hi again. This is the second part of the EDA module. This one is devoted to multivariate analysis. And before we go into specific techniques, I want to spend a few minutes talking about the challenges we encounter when we deal with multivariate situations. And multivariate situation is not just a simple scaling up from univariate or bivariate situations. And that's often lost in the shuffle. It's very easy to jump to these techniques and start analyzing, but it's not always that effective because of these problems with multivariable data. And then I'll just go over some basic charts and graphs, things that you might be familiar with, but I'm assuming some of them you're not that familiar with, so I'll spend a little bit of time on this just to make sure everybody's on the same page. And then at that point, between the different types of maps and the different types of EDA views, you have the tools to actually start exploring the data for simple patterns. Then from next module on, we'll move into a little more formal analysis dealing with spatial autocorrelation. So one of the major problems related to multivariate analysis is called the curse of dimensionality. And this term was coined, very early on in 1961 by Bellman. And in essence, it means that what works in small dimensions, 1, 2, 3, doesn't necessarily work in large dimension. And with large dimension, we're talking about hundreds or thousands of variables. In some commercial applications, millions of variables. So what the curse means is that a technique that works very well, say for 2 or 3 variables, either totally breaks down or becomes unmanageably complex in the sense that it takes forever to compute in higher dimensions. And the original example of Bellman, and I still really like it because it illustrates let me show this first. It illustrates some of the complexity. Let's say we have a function and we try to find the maximum of the function. One easy way to approach this is to take the range. It's a very simple problem. We take the range on the x-axis and divide it in equal intervals and then compute the value for each of these intervals, and then by examining the values, we know that the maximum will be in this kind of range, and then we can repeat the process. But just for the sake of the argument, let's say we have 1 dimension and we divide it in 10 intervals. Now what happens if we go to 2 dimensions? So 2 dimensions here, we divide the x-axis in 10 intervals, we divide the y-axis in 10 intervals, but now we have 100 observation points. In 3 dimensions, we get 1,000 observation points. In general, in k dimensions, we will have 10 to the k observation points. And even for not so large a problem, say with 10 variables, 10 dimensions, k10, we need 10 billion evaluation points. So this is an example of a technique that works perfectly fine for 1, 2, 3, maybe 4 variables, but breaks down in higher dimensions. That's the curse of dimensionality. And we'll see the curse of dimensionality, for example, when we deal with k nearest neighbor searches. That's also a technique that doesn't work that well when k becomes too large. This curse of dimensionality we will encounter frequently in the second course, the course that deals with spatial cluster analysis, where a lot of the focus is on multivariate analysis. Okay, so the second big problem for multivariate analysis is what is called the empty space problem. And the empty space problem, we don't necessarily think of this when we work in 2 dimensions or even in 3 dimensions, but high dimensional spaces are exceedingly sparse. There's a lot of distance between the data points. And also there's some weird things going on, and this is a little bit technical, but once you start thinking about 4-dimensional and 5-dimensional and 6-dimensional spaces, we have a hard time imagining this. Maybe some people can, most people can't. But one of the characteristics of the data points in such spaces is they tend to move towards the edges, and that complicates this empty space problem, and it definitely complicates the search for clusters of like observations. So to illustrate this empty space problem, I have this simple example here. We'll see this plot in a little bit. This is a parallel coordinate plot, but it shows on each single dimension 10 randomly spaced points. So we generate 10 random numbers and we see where they are on the axis. And so on one dimension, these points are all still fairly close together. But even if we go to something as simple as 3 dimensions, these are the same 10 points floating in a data cube. And you see all this empty space, all this black stuff in between the yellow points. And that is the problem, the empty space problem. Because what does that mean? If we're looking for points that are close together, we have to traverse a lot of space before we find them. And that is very inefficient, and it affects our methods for cluster detection and so on. So 2 kind of larger principles to keep in mind: curse of dimensionality and the empty space problem. So what are we then trying to do in multivariate EDA? Since we cannot very well represent data in 4 and higher dimensions, we have to think about ways to represent these same data points, these data tuples as we call them, on a screen, on a flat screen or on a flat piece of paper in 2 dimensions. So how this works is by reducing the dimensions in some fashion, or by projecting the data in some fashion, or by using some clever graphical tricks like a parallel coordinate plot, as we'll see in a little bit. So the purpose then, once we have devices, as I've been calling them, to represent these multivariate data points in 2 dimensions, is to find structure, interaction, and patterns between the data. Very much the same purpose as what we have with univariate and bivariate data, but with multiple variables, the importance of interaction among the variables increases. The methods that I'll cover, a subset of the range that is available, but a subset that I found very effective in my own work: bubble charts, 3D scatter plots or data cubes, parallel coordinate plot, and conditional plots. We've already seen a form of conditional plots in the conditional map or the micro maps that we saw in the previous module. Now we'll extend this to standard statistical graphs. Important. This is exploratory data analysis. And I mention this because this is sometimes lost in the shuffle. We get excited, we have all these different tools now, we can go at it, we can analyze the data. But remember IJ good. It's potentially explicable patterns. No hypothesis tests, no p-values. So exploratory methods do not explain anything. They suggest hypotheses and they suggest potentially interesting patterns. But there is a next step, the confirmatory step. We don't deal with that in this class, but it's important to remember you are not done with the exploratory data analysis. It's just kind of the first stage in what I like to see as an evolution of increasing sophistication and increasing formalism of your analysis. And most of the time, there are no p-values. Now, we have already seen 2 instances where we do have p-values, namely where we did the difference in means test with the averages chart and where we did the chow test on the constancy of the slopes. So those are exceptions to the rule. A purist EDA person doesn't want to hear anything about hypothesis tests or p-values. Okay. What are some of these tools? As I mentioned, 4 of them, starting with the bubble chart. The bubble chart is, in essence, a scatter plot on steroids. And a scatter plot, as we've seen in the previous set of slides, deals with two dimensions, x and y axis. Now, when you start thinking of the points in the plot as a shape that can be manipulated, then we're in business. Then we can use, let's say we represent a point not as a point, but as a circle. Now we can make the size of the circle, or the area of the circle, proportional to a third variable. And then we can start looking at the interactions between the slope of the two variables on the x and the y axis with this third variable that is represented as the size of the bubble, so to speak. And then we can also go a step further and introduce a fourth variable in the color shading of the bubble. Now, this is a bit challenging for human perception. Some people have trouble with colors, and colors can be very misleading, as we've seen in the discussion of maps in the previous module. But so you get the principle. The principle is we go beyond the scatter plot as a plot of points to the scatter plot as a plot of circles. Circles whose size, area, radius we can manipulate as a function of a third variable, and we can also shade or color as a function of a fourth variable. And we'll see two examples of this, one where we stick to three variables and one where artificially we go to four variables. And as it turns out, again, the bubble chart can be used as a way to look at spatial heterogeneity, to look for structural breaks if the selections in question are spatial. That's the same principle we just saw in the previous set of slides. So here's an example of a bubble chart. You may be familiar with this. There's lots of these out on the web. What's going on here? So this is the same regression, the same scatter plot I've been using in a number of examples. This is for 55 neighborhoods in New York City. On the x-axis, we have the percentage households with children. So as this percentage goes up, these are neighborhoods with a lot of children. These are neighborhoods with very few children. And then on the vertical axis is the percentage of households that receive public assistance. So on the low end, very little public assistance. On the high end, a lot of public assistance. So up in this corner, these are neighborhoods with a lot of children that get a lot of public assistance. Here, very few children, very few public assistance. This is the linear slope that we saw. This is the same scatter plot as what we saw in the previous set of slides. Now, instead of having points, we have circles. And in this particular application, both the size and the color of the circle are the same variable, just to bring things out a bit. And the color shading, the legend, so to speak, is a diverging legend. You may remember this from the mapping module, and it is a standard deviational diverging schedule legend. So the brown to red values are above the mean, the light blue to dark blue values are below the mean. So these circles, these big circles, are the high rent areas. And what this bubble chart brings out is an interaction between the rent and the size of the number of children in the families and the degree of public assistance. So these four, or actually I think there's five, there's six of them. See here, six. These six neighborhoods are all in Lower Manhattan, as we've seen in the mapping chapter. It's the same data set. And so then we have an interaction between the high rent, but we don't have causation. We don't know what the direction is. We don't know whether it's a high rent area because there are few children, and we can think that high rent and public assistance are correlated, because if people can pay high rent, they don't need public assistance. But as such, this graph does not provide any insight into causation. What it does provide is suggestions of interactions, of hypotheses that we then can examine more formally, and that's the whole spirit of EDA. So this is a kind of a standard application of a bubble chart, where you just use the size of the circle as the third variable. A slightly different application is this particular one, where I cheat a little bit, in that I have 4 variables, although you don't see it. You only see 3 of them. One variable is a constant, and so I use the third variable, the size of the circle, to set to a constant, and then I use the fourth variable, in this case a spatial selection based on Manhattan and the Bronx versus the rest, as the color for the bubbles. So this approach is yet another way to look at potential structural differences. We saw in the brushing of the scatter plot how we could compare the 2 regression lines, also more formally through a Chow test. In this case, we can compare the overall pattern between the 2 subgroups, and it's spatial heterogeneity because they're spatially selected subgroups. We compare them by means of the different colors. So the dark colored ones are in Manhattan and the Bronx. And what we see here, if you look carefully, is that there's really a split between the Manhattan neighborhoods and then the ones up here, which are among the higher assistance and the higher, more kids, which tend to be in the Bronx part of that part of New York. So this is an example of using the bubble chart to assess structural change, spatial heterogeneity. Bubble chart, very simple. Scatter plot on steroids. We introduce an additional dimension or 2 additional dimensions by manipulating both the size and the color of the bubble. 3D scatter plot, you may be familiar with, is basically a data cube. Instead of 2 dimensions, we have 3 dimensions, so we have a cube. We can always project the points in the cloud, the data cloud, project them on the side panel. Then we have a regular scatter plot for any combination of the combination of 2 out of the 3 variables. But if you've ever worked with this, with a 3D data cube, you might know that it's not that easy, because it's not really 3D. You are not in virtual reality walking in a 3D data cloud. Now, I could talk about that too, but unfortunately at this point, GeoDa doesn't yet implement this. So it's, in essence, the 3D scatter plot is projected onto a 2-dimensional screen or a 2-dimensional piece of paper. And so as a result, the issue of perspective is critical. And you get around that by rotating the cube. And by rotating the cube, you look at the data cloud from different perspectives, and you start to reconstruct a true 3D vision in your brain from the different projections of perspective plots, really, of the 3D cloud. And let me show you a little illustration. So this is the same data, the same 3 variables. Rent is Z, and then kids is X, and public assistance is Y. And X and Y, this is our scatter plot projected on the bottom panel here, X-axis, Y-axis. So this data cloud has been projected down onto these little points here, and this is if you remember, this is kind of the linear plot that we just saw also in the bubble chart. The difficulty with this is that, as I mentioned, in essence, it's a projection on the flat screen, but we don't really know where these points are in 3D, and that comes into play when we try to do brushing and selection. So as you'll see in the lab notes, GeoDa has a way of creating a selection box, this little red cube, and then you move that around in the space. And you might think, okay, we're trying to get, so what I'm trying to do is I'm trying to get at these points here, and from this perspective, it looks like these five are very close together, and then this one is quite a bit further away. Now here we're looking at this from a different perspective, and we might think, I mean, when you look at this box, it looks like it's selecting all these points in 3 dimensions, but only one of them is yellow. And in GeoDa, the selected points, the default is that they turn yellow. So you might think that you have it, but in fact you don't. And you can see this very clearly when you rotate the cube. Then you see, hey, I'm here. I'm way away from these points. But because I was looking from this direction, it looked like they were all in the box. And in fact, they were not. So if you play with this a little bit, and it does take some practice, and it's, I mean, for me, it's actually quite fun to do this, but it's also sometimes not that intuitive. But after some trial and error, finally I've got my box around the points and I have them all selected. And of course, linking and brushing, once you have these points selected, you can also see them on any other view that's open, and the reverse works as well, where, you know, spatial heterogeneity, we select on the map, and as we change the selection on the map, the yellow points get highlighted in the cube. And then of course we'd be interested in situations, and we already know this is the case, where these points, these 6 points that are very close in multi-attribute space, are also very close in geographical space. And this is a theme that will come back over and over again. The match between attribute similarity, in this case closeness in a 3D data cube, and geographical similarity, where they are on the map. Parallel coordinate plot. Probably something you are less familiar with. Very clever device, because so far we can only really deal with 3 or at most 4 variables with the bubble chart. We introduced a 4th variable. Obviously in the 3D data cube you can only go through 3 dimensions. What happens if you need 4 or 10 or 20 variables? So this parallel coordinate plot was developed by Inselberg in the early 80s, had this really clever idea of, rather than representing the axes as perpendicular axes, I mean, if you think of the data cube, each axis is perpendicular to another axis. Instead, you represent the axes as parallel lines. So now, rather than having a point in multi-attribute space, you have a data point on each of the parallel axes, and an observation is represented by a line that connects all these points. So the line in the parallel coordinate plot is the counterpart of the point in a multidimensional data cube. The advantage is, of course, that once you go over 3 dimensions in a data cube, you're out of luck. Whereas with the parallel lines, you can keep going. Let me illustrate this. So here's our same example again. And I do this on purpose because I can then show the similarity between the points in the data cube and the lines in the parallel coordinate plot. But let's look at this a little closer. So each variable is represented by a parallel line. Each observation has a value for each of the parallel lines. So let's look at this observation. Has a value here on the kid's axis, and a value here on the assistant axis, and then a value way down here on the rent axis. So the observation is the line. We can select observations by selecting lines. We can brush this plot. Most importantly, we use the parallel coordinate plot for something called visual cluster detection. And let me illustrate this. So what are clusters in a parallel coordinate plot? Remember, clusters in a 3D scatter plot, we just saw one. This is an example of what could be a cluster. These are points in three-dimensional space that are very close together. So if we go to an observation as a line, then a cluster in a parallel coordinate plot will be lines that are close together. So lines that are follow the same path and are close together correspond to points that are close together in multidimensional space. For 3 dimensions, you can clearly see it. For higher dimensions, you just have to imagine it because you can no longer visualize the higher dimensional data hypercubes, so to speak. So this is used for visual cluster identification in the sense that you look for lines, each set of collection of line segments corresponds to an observation. You're looking for these line segments that follow the same pattern, and that's called visual cluster identification. Of course, this doesn't work very well with, just like a scatter plot doesn't work very well with very large data sets. So there's all kinds of tricks to remove the clutter, to simplify the graph, to bring out, just like we smooth the scatter plot, you can do something similar with the lines on the PCP if you have many observations. We don't pursue that here, but there is a very large literature on technical aspects of how to implement this visual cluster identification in a parallel coordinate plot. So here's my illustration. Here are our same points again. We see these are fairly close together. This one is still close relative to the rest, but it's not as close. And as it turns out, these 5 points correspond to these 5 line segments, very close together. The other one is still fairly close, but is a little bit off on 2 of the dimensions, on the kids and the assistant dimension, and then it kind of converges to the same high rent. So this is an illustration of what a cluster is in a parallel coordinate plot and how that corresponds with points that are very close together in a data cube. Then the notion of an outlier is the opposite. So whereas clusters are lines that are close together and follow the same path, an outlier is a line that is far away from the main pack. And that is the counterpart to a point that is far away from the core of the data cloud in a high dimensional hypercube or hyperspace. So just like we had visual cluster identification, we now have visual outlier identification. And let me again illustrate this in a 3-dimensional example, the same example. We have this line here, which corresponds to this point way in the corner, far away from everything else. It's kind of a strange point because it has the maximum for the percentage kids, it has the maximum for the public assistance, and then it has the minimum for rent. Now, if you recall in our earlier illustrations, for this rent variable, we had 3 observations that had a rent of 0, and this is picked up by this dramatic drop in the line. So this is a point that is, far from the core of the data cube. You could say, well, these are also far. They are. So in a sense, as a group, they are outliers, but as a subgroup, they are a cluster because they're so similar. So visual cluster detection, visual outlier detection, it's an art as well as a science. There are several additional techniques to help you with this, but here's an example I actually cheated a little bit, and this will come back later, actually in the second course. So this is moving from 3 variables to 5 variables. And I have visually detected these kind of common patterns between the lines. Actually, as I said, I cheated. What this is the representation of 6 observations that are identified as a cluster using k-means clustering. And k-means is a well-known technique of unsupervised learning where you find clusters of observations that are similar on multiple variables, multiple dimensions. That's exactly what we're trying to do here in a visual way. So you can also flip it around. So on the one hand, you can say we're going to do visual cluster detection and try to find the clusters by an examination of these lines. And as I said, there are much more sophisticated ways of doing this than just kind of eyeballing it. And then we can also flip it around and say, after we identify the clusters by means of one of the many multivariate cluster techniques, what does this actually mean in terms of the variables and the values for the variables, different variables for the observations that are contained in this cluster? So we call every line, the set of connected lines is an observation. These are all the observations in this cluster identified by k-means. As it turns out, in this particular example, these are also, again, the same neighborhoods in Manhattan that we already saw before. So they are very similar both geographically as well as in multi-attribute space. Parallel coordinate plot. The next one is we've already seen in a form. We've seen conditional maps in our micromap matrix. The idea behind a conditional plot, just to recall, is that you are creating subsets of the data according to conditioning variables, where you create subintervals of the conditioning variables to limit the data, and then for each of these subsets of the data you create a separate plot. As I mentioned in the previous module, this is known as a trellis display or small multiples. Our ggplot calls these facet graphs. The essence, these are all the same thing, all different terms for the same thing. We've already seen the conditioning on the axis, and then we end up with a matrix, in essence, of microplots. One plot for a subset of the data as determined by the categories on the axis. And just like with the micro maps, how do you interpret this? If the plots are similar, there's no effect of the conditioning variables. If the plots are different and they show different patterns in different subsets of the data, then that suggests an interaction of the conditioning variables with the actual variable of interest. Again, no causation. It's just a suggestion of interaction. So we've seen this before. I'll show 2 examples. So in GeoDa, you can do this for histograms, scatter plots, and box plots. One example is using a scatter plot. So this involves 4 variables. The bubble chart also involves 4 variables. The 3D scatter 3 variables, parallel coordinate plot as many as you can handle, and here again with the scatter plot, 2 variables of interest for which the plot is constructed, and then 2 conditioning variables. In this case, I have 2 sub-intervals on the horizontal axis and 2 sub-intervals on the vertical axis. And so what are we looking for? We're looking for similarity and differences. Now, take this with a grain of salt. This regression is only based on 3 data points, so it's just to illustrate the principle. In essence, between these 2 areas, in the lower part of this conditioning variable, no difference. But in the higher part of this vertical conditioning variable, we go from a positive and non-significant slope to a negative slope. But also, again, keep in mind, this is based on very few observations. So that's is just to illustrate the general idea. What you're trying to do is create subsets of variables that you think might be interacting with the variables of interest. And then if there's no interaction, all the slopes should be the same. If there is interaction, as in the suggestion is here, these slopes are very different. So that's the kind of classic example of a conditional scatter plot or a trellis graph. And then, of course, from my perspective, I'm always thinking, how can I exploit these kinds of techniques to address my two major concerns, spatial dependence and spatial heterogeneity? And for this one in particular, there is a way to exploit the conditional box plot to look at, again, spatial heterogeneity in terms of the form of the shape of the distribution, but primarily the central tendency, the means or the medians. As before, the critical distinguishing aspect is that the selection is spatial. If it is a non-spatial selection, then there's nothing spatial to it, as we've already seen many times. So let's see what this looks like. We have a selection as reflected by a categorical variable. 1 is the selection, 0 is everybody else. This is the rent, this is not the rent, this is the percentage kids, and as we've already seen in several of the earlier examples, the neighborhoods in Manhattan don't have very many kids in them, and they have high rents and all these kinds of things. So what this particular graph shows is that the median for the unselected, the 0, is much higher than the median for the selected. And same for the means. The means are affected a little more by outliers. So there, in this case, the mean is under the median, and in the Manhattan case, the mean is above the median because of these points pulling it up. What we also still see is that the spread, because these vertical axes are the same for both box plots, the spread for the neighborhoods in Manhattan is much larger than the spread in the rest. In essence, you look at whether these, the range around the median between the two distributions shows as little overlap as possible. If there's a lot of overlap, say if the distribution for the selected was like this, then you could not really say that there's a difference in medians. In contrast to what we saw for the averages chart, there is no formal T or F tests here involved. It's purely eyeballing. But this is often very useful, again, in the context of cluster analysis, which we'll see in the spring. If you have say 6 different clusters identified, and you want to see how that translates into the distribution of particular variables that you either included in the cluster exercise or did not include in the cluster exercise. Both cases are equally interesting. So this allows you to do conditioning on categorical variables. In the lab notes, that's elaborated on how to exactly do that in GeoDa, but we have categorical variables. In the clustering case, each cluster would have its own category, and you could see how the distribution of the variable of interest is the same or is different between different subclusters of the data. And as I mentioned, you can do it both for the variables involved in the clustering, or you could do it, say, for a policy variable. After you have clustered neighborhoods in terms of similarity, then you can look at how is this policy variable distributed between the different clusters. This is spatial heterogeneity when the selection is spatial. So this concludes my quick, as I call it, the primer of multivariate EDA. There are the basic tools that you have now at your disposition to explore the data. We saw the bubble chart, the 3D scatter plot, the parallel coordinate plot, and the conditional plots as ways to represent multivariate associations, in essence, in 2 dimensions on a flat screen or a flat piece of paper. So in these first couple of modules, we've basically covered some very descriptive exploratory techniques, the basis for carrying out dynamic interaction with the data. Starting with the next module, we move into a little bit more formal terrain with a discussion of spatial autocorrelation. See you next week.